Alright, in this session we're going to talk about exact trigonometric ratios for any angle. This is section 2.2 for those of you following along in your textbook. So exact trig ratios for any angle. Okay, this is going to tie into some of the earlier things that we talked about, like reference angles and that sort of thing, and the different quadrants. The first thing we're going to mention before we dive into some examples is what ratios are positive and negative in which quadrants. So let's look quickly at a couple of given angles. So let's start with an angle in the first quadrant. If I think about this like a right angle triangle, then I'll call these X, Y, and R. In the first quadrant, X is positive, Y is positive, and R is positive. That means that all of the ratios that I set up are going to be positive, and in quadrant 1, the sine of my angle, the cosine of my angle, and the tangent of my angle are all positive. If I come over to quadrant 2, however, R is always going to be positive wherever you're at. But in quadrant 2, X is negative and Y is positive. And if I think about a triangle based on those, sine is opposite over opposite over hypotenuse. Those will both be positive, so the sine value will be positive. Cosine is adjacent over hypotenuse, negative over positive, so that'll be negative. And tangent is opposite over adjacent, which would be positive over negative, so that would also be negative. By the way, these results are also summarized on page 90, and they've got a little bit more room to work with there, so you may also want to look at those there as well. Following the same sort of logic, in quadrant 3, sine is the opposite side over the hypotenuse, or a negative over a positive, so it's negative. Cosine is an adjacent over hypotenuse, or a negative over a hypotenuse, so it's also negative. Tangent is the opposite over the adjacent, or a negative over a negative, so it's positive. And lastly, in quadrant 4, following the same logic, sine would be the opposite over the hypotenuse, so a negative over a positive. Sine would be negative. Cosine of the angle would be the adjacent over the hypotenuse, positive over positive. And tangent would be the opposite over the adjacent, negative over positive, or negative. You can think of it a little bit as what's happening with X and Y. X sort of links up to your cosine, Y links up to your sine, and tangent is the ratio of the two. In the first quadrant and the fourth quadrant, X is positive, so cosine will be positive in both those places. In the first and the second quadrant, your Y value is positive, so sine will be positive in both of those quadrants. And the ratio Y over X is positive in quadrants 1 and 3, so that's where tangent will be positive. Another short form that's put into this is the cast system. Cosine, all, sine, tangent, which sort of tells you what's positive where. All the ratios are positive in the first quadrant, only sine in the second quadrant, tangent in the third quadrant, and cosine in the fourth quadrant. Now, in any case, the angle that you're interested in, and I'm going to show this with one of the special triangles we had the other day. If I make a 150-degree angle here, and my reference angle is 30 degrees here. And if I worked out the results I had from the other day, the sine of 30 degrees is equal to 1/2. The cosine of 30 degrees is equal to √3/2, and the tangent of 30 degrees is equal to, it would be 1/2 √3/2 over 3 over 3 over 3. √3/3. Now, what this tells me about 150 degrees is that the ratios will be the same, but they're going to be positive or negative depending on the quadrant they're in. My angle terminates in quadrant 2, so my sine value is positive, so sine of 150 degrees is just 1/2, same as the sine of 30 degrees. However, in quadrant 2, cosine should be negative. So that means the cosine of 150 degrees is negative √3/2. Similarly, tangent will be negative in that quadrant, so the tangent of 150 degrees is negative √3/3. So, in general, if you're looking at figuring out the trigonometric ratio for an angle greater than 90 degrees, you make a setup like this and figure out what your reference angle is. Talk about sine, cosine, and tangent of the reference angle, and then match that up to your original angle, just switching the sign depending on which quadrant you're in. Okay, a few examples of working with this. So this will be example 1 from page 91. The point P (-815) lies on the terminal arm of an angle theta in standard position. Determine the exact trigonometric ratios for sine, cosine, and tangent of that angle. So first of all, this notation, P (-815), if you see that, that's referring to a coordinate point. So my point is, give myself enough room to work with. This is a terrible straight line. Two. 8. 15 here. And my point at -8 and 15 would be about there. And we were told the point, -8, 15, lies on the terminal arm for an angle. So I draw a line out to here, roughly speaking. And this describes the angle I'm interested in. That's my angle theta. So what I'm going to end up working with, however, is my reference angle in here. So, in this right angle triangle, I know this side is 8 units long, and this side is 15 units long, meaning that the hypotenuse is going to be the square root of 15 squared plus 8 squared, which turns out in this case to equal 17. Okay, what I can say from here. The sine of my reference angle. Sine is opposite over hypotenuse, so the sine of my reference angle is 15 over 17. The cosine of my reference angle is adjacent over hypotenuse, or 8 over 17, and the tangent of my reference angle is the opposite over the adjacent, or 15 over 8. Now since I'm in quadrant 2, this means the sine of my original angle, the sine of this thing, sine should be positive in quadrant 2. So it's going to stay 15/17. The cosine of my original angle, in the second quadrant cosine should be negative, so this will be negative 8/17. And tangent in the second quadrant should also be negative, so this will be negative 15/8. And those are the answers to the question. Those are the primary trigonometric ratios for the angle drawn out by a terminal arm with the point -8 and 15 on it. Alright, a few more examples. In example 2, on page 91, we're asked to determine, and we talked about this a little bit last time, but this will be a bit of a refresher, determine the exact value of cosine 135 degrees. Now, to refresh people, we had shown last time that if you had a right isosceles triangle with a hypotenuse of 1, you could show each side was root 2/2 long. Now, if I show 135 degrees, in standard position, it's going to look something like that. So to talk about cosine, I am going to look at the reference angle, 45 degrees. Now, if I happen to have a hypotenuse of 1, I know the two sides are going to be root 2/2 and root 2/2. So based on either of those triangles, I can say the cosine of 45 degrees is root 2/2. So the cosine of 135 degrees in the second quadrant, cosine should be negative, so it'll be negative root 2/2. Moving onward, example 3, page 92. We are told to suppose theta is an angle in standard position with a terminal arm in quadrant 3 and the cosine of the angle is negative 3/4. What are the exact values of sine and tangent of the same angle? Okay, so we draw this out. We've got an angle drawn in standard position that ends in quadrant 3. So it ends up down here, and its cosine value is negative 3/4. And remember, cosine we could think about as the adjacent and the hypotenuse. So if I draw a right triangle down here in quadrant 4, the way this is the entirety of the angle that we're talking about, angle theta. If cosine of theta equals negative 3/4, then my triangle that I've got here has got sides, adjacent side 3, hypotenuse of 4. Working backwards, Pythagoras would tell me this side is the square root of 4 squared minus 3 squared, or the square root of 7. So, now I can think about this triangle and my reference angle theta r. The sine of theta r would be the opposite side over the hypotenuse, or root 7/4. And the tangent of my reference angle would be the opposite over the adjacent, or root 7/3. In quadrant 3, sine theta is negative, Therefore, sine theta is negative root 7 over 4. And in quadrant 3, tangent is positive. Therefore, tan theta is the positive root 7 over 3. So, given what cosine was and what quadrant we were in, we could figure out for our reference angle what sine and cotangent were, and then based on the fact we're in quadrant 3, we could decide whether those values should be positive or negative. Okay. Example 4 on page 93 introduces a term called a quadrantal angle, which is a fancy way for saying something that lies right on an axis. Angle, when shown in standard position, has a terminal arm on an axis. Some examples are 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees, and so on. And in this particular example, we are asked for the quadrantal angle 90 degrees, determine sine, cosine, and tangent. And if I think about trying to draw a triangle up there at 90 degrees, so my terminal arm is lying right on the y-axis. There's my 90 degrees. An earlier triangle down here, thinking about x, y, and r, pulling this triangle into here, my x goes to 0, my y goes to whatever y is, and my r goes to whatever y is. Basically cramming this triangle back onto a straight line. Sine is going to be opposite over hypotenuse, or y over y, which equals 1. Cosine of 90 degrees is going to be adjacent over hypotenuse, or 0 over y, which is 0. And the tangent of 90 degrees is going to be the opposite over the adjacent, or y over 0. Now, what happens when you divide something by 0? Math explodes. So basically the tangent of 90 degrees is undefined. There is no value for a tangent of 90 degrees. If you go to your calculator, if you do sine 90, it should give you 1. If you do cosine of 90, it should give you 0. If you do tangent of 90, it should give you undefined. And if you use that to think about the other quadrantal angles, for 180, things just end up reversing a bit. Sine of 180 is 0. Cosine of 180 is negative 1. And tangent of 180 is 0. For 270, the sine value is negative 1. The cosine value is 0. And the tangent is undefined. And at 360, sine is 0, cosine is 1, and tangent is 0. example 5 on page 94. Solve for an angle given its exact sine, cosine, or tangent value. So we're given a couple of examples here. So if sine theta equals a half and theta is between 0 and 360 degrees, solve for theta. So if we think about those special triangles we talked about last time, there was one case where the sine of an angle came up to be 1/2. That was when we had the 30, 60, 90 triangle. Without going through everything again, side ended up being a half, √3/2, and 1. So we know that the sine of 30 degrees works out to be a half. But since this is asking for everywhere between 0 and 360 where you get a positive sine value of 1/2, that's going to happen in quadrant 1 with an angle of 30 degrees, but it's also going to happen in quadrant 2 off a reference angle of 30 or an angle in standard position of 150 degrees. It's not going to work in the other two quadrants because those sine values would be negative. And I would say that based on these conditions, my angle could be 30 degrees or 150 degrees. B part of the example, similar sort of setup, only now we're given the cosine of an angle is negative √3/2, and the angles between 0 and 180 degrees. Well, a cosine value of √3/2 also ties us back to 30, but since it's a negative √3/2, that's going to happen in quadrants 2 or 3. I'll draw that out again. So based on what my cosine value is, I know my reference angle's got to be 30, and since it's negative, that could either be 30 degrees here or 30 degrees here. This would give me angles of 150 degrees or 210 degrees, but since I have to restrict myself to be between 0 and 180 degrees, the only angle that works is 150 degrees. So if you're given sine and cosine values that you recognize from those special triangles we worked out, then that can tell you what the reference angle is, and then you just have to match up to whether it's positive or negative and which quadrants those meet. Right. One last example. And this is example 6 on page 95, which is similar to example 5, only you're going to use your calculator a bit more in this case. So in this we're told the cosine of our angle is equal to negative 0.6753. That is not something nicely from one of our special triangles. And our angle is between 0 and 360 degrees. So to get my starting point, I'm going to go to my trusty calculator. I'm going to make sure I'm in degree mode since I'm working in degrees. I really feel at this point that I should say Sam. It's been such a tradition up to this point. So my angle I can start out as talking about is the inverse cosine of negative 0.6753. And when I do that, inverse cosine of negative 0.6753, my calculator tells me we have an angle of about 132, and we're asked to record this to a tenth, so 132.5 degrees. But your calculator is only giving you one possibility. it is worth thinking about how these things work in our different quadrants. (132.5 degrees) is going to be somewhere up here. With a reference angle of 47.5 degrees. Now, my cosine value is negative. And we say cos theta is negative in quadrants 2 and 3. So that means I got to think about the same angle down here. If I come down here, 47.5 degrees, then that angle gets a little crowded at this point, I apologize, all the way around would be at 180 plus 47.5, or 227.5 degrees. So, to have a cosine value of negative 0.6753 between 0 and 360 degrees, your angle could be 132.5 degrees or 227.5 degrees. And if you check, you can double check these ones easily enough, because you can just go to your calculator and show that the cosine of 227.5 is negative 0.675. Well, 6 rounding at the 10,000ths place, because we rounded these off to tenths. Okay, that will probably have seemed a little confusing if you're watching it through for your first time. There's a lot of stuff to kind of take in there. Please feel free to shoot me off any questions you got or anything you'd like a little bit more clarity on. There'll be some sample practice work to go along with this in the Google Classroom. That's all that I have for right now. Thanks for your time, everybody.